Hey guys, and welcome to this video where I am demonstrating modeling, big data modeling in MySQL versus MongoDB. Now, this is probably a topic you might have heard often, where we talk about SQL versus NoSQL systems. MongoDB is a document store or document data-oriented database, which is generally classified as one of the NoSQL databases. It is pretty popular. It's the most popular NoSQL system out there, and it's able to scale to petabytes and billions of records. MySQL, on the other hand, is a tried and tested relational database system. And what we want to see is take a use case and model it in these two databases. The words we hear often will be normalized and denormalized, but we're just going to talk through all those ones. And we are going to do it over a data set that spans into millions. By the way, these databases can really scale horizontally across many machines. But in this video, I am using one workstation to handle everything at once. Okay, let's talk about the objective. Just four things I want to do in this demonstration. Number one, discuss modeling in MySQL versus MongoDB. Then once we've highlighted that, we are going to implement it using Apache Spark and how we take the same data that have been loaded into MySQL in a relational design, how we can do it in a denormalized design in MongoDB. Then we will we'll try to achieve the same results in these two databases, aggregation queries. So we're going to write aggregation queries that we're quite familiar with in MySQL, then we do the same in MongoDB as well. Then I'll talk about the new cool thing that MySQL is incorporating, and that's adding the capability for deploying MongoDB as a document store, as well as what we've always known, using it as a relational database. Okay, so that is what we're trying to achieve right now. Let us take a look at the use case that we want to use for this demonstration. So on the website, let me show you that. Yes, this is the Open Data Gov initiative, and this is the Ministry of Transport anonymized test results. So basically, the test, they do vehicle testing, right, to see if they're roadworthy, and if they pass or they fail, they try to give the reason for the failure as well. And these guys have been keeping this data for a long time, literally since 2005 till 2017, I think. And that's a lot of data. For example, I have used the 2005 and the 2010. 2005 we have now 7.4 million records, and 2010 over 50 million records. And trying to achieve that in a single workstation just gives us that kind of big data problem we were looking for. Okay, so what we'll jump right now is we want to take a look at the design. So if you read through this document that you can download from the website, you see all the talk about what the testing is and what the data structure is all about. So it has quite a number of lookup tables. And you see test outcome lookup table. We have test type, fuel type, test item data, reason for failure. It could be failure, it could be pass, advisory note. Then let me just go straight to the entity relationship diagram for the data set itself. So we have a test result. So once we do testing, we get a test result, and a test result may have one, zero, or more test item. So they wrote one here, but data tells me it's zero. So if the test passes, it's not going to have test items, right? Because there's no item in the vehicle that failed the test. So test items is literally the ones that failed, right? So a test item will belong to one test result, but a test result can have multiple test items. Now a test item is always defined by a test item detail. Then the test item detail has a parent test item group, and test item groups are self-joined in a hierarchy, right? So you can have one test item group is going to be a parent to many test item groups that themselves are going to be parent to many other test item groups. So it's like a tree. right? Then test items also, the items that failed in the vehicle can be located somewhere. So the failure location is used to define the location of the test item on that vehicle. So this is a very good entity relationship model that really highlights what we're trying to talk about modeling, because right here we find joins, we have one-to-one relationships, we have many-to-one relationships, we also have many-to-many relationships. Basically everything we're trying to do is here, right? And the good thing about it is also is that with the data set we were giving the structure of the table as well as the DDL to build the table. So it's going to be easy. You can just copy this DDL to build the table and use this DML, this load data statement, to populate the table with whatever the data you've downloaded. I've made things easy because I have also provided the whole DDL and DML in a script, so you literally can create a database in MySQL and create these tables, and you can see with the indexes all set, so it makes it really nice. You can just get up and running. If you want to run it definitely once you've downloaded the data and unzipped it, especially the lookup data and everything, you want to change this path to make sure it's to the path that you've downloaded the data. Okay, so I have done that, and if I go to the my database, this is my MySQL database. I hope you can see my screen. I can use MOT, and these are all the tables you want to find there, right? So these are lookup tables. Then I loaded for 2005 and 2010. So if I try to find out the number of record I have in 2005, like I said, it's about 7 point something million record. Let's see. Okay, so test item is 9.8 million records, and test results, yeah, test result is 7.4 million records. This is just for 2005, and remember, it's a for a test result you can have 0 or more test items. So the relationship, everything has been built in, right? Let's see for 2010. Okay, so we have about 36 million test results in 2010. Having all this right here, we want to model this data into a MongoDB dataset. So for us to model it into a new environment, I kind of redrew the entity relationship diagram to show all the fields inside and the relationship. This diagram, however, is lacking the definition of the relationship. So they're just arrows, but it doesn't tell us the notation, whether it's one-to-one or one-to-many. So let's talk about putting the same thing into a MongoDB database. Right, MongoDB is a document data store, horizontally scalable, it is consistent and partition tolerant. It doesn't support joins, so we cannot have the relationships defined in a database, right? And data is stored as JSON documents. And when you say JSON documents, it means it can contain very rich nested structures that we don't have in a relational, in a flat relational structure. So we've seen what it looks like in a relational table. Let's talk about what it should look like in MongoDB. First and foremost, when you design for MongoDB, you have to think about the context, right? And the context means the use case. Am I designing for a transactional workload, or am I designing for an aggregation workload, right? So if you're doing for reporting, so aggregation, an analytical job, your design will be different than if you're doing the same thing for a transactional workload. And I'll give you a typical example. So let's say you're doing something like a social media stuff, and you have users and you have posts, users and posts. If you're designing for transactional workload, that means you always want to associate the user with a post. Now in MongoDB, so I'll go to number 2 quickly because it's going to help me explain number 1. In MongoDB, there are 2 ways you can do modeling. You can think in terms of references, so document references, or you can think of document embedding. right? So embedding is when you take the document and make it a part. It's like denormalizing. So you make it a sub object or an object within the document, a document within another document. And that will be for a one-to-one relationship. If it's for a one-to-many relationship, you make a collection of all those objects, an array within your parent object. That's embedding. But if you were doing referencing, you would use what we call dbrefs, and I'll show you that as well. So you have to think of this. Now, the context matters. So let's go back to our social media example. If I embed the user in the post, it's easy to write, it's easy to read, right? However, if the user makes a change to his name, which is very common in that kind of application, you will have to look for every case where there was a post for the user to make that change. Now, that is not efficient. So what you'd use in that transactional use case will be object referencing, where you pick up a post and you use the object ref or the DB ref to find the user that made the post. So this is a normalized scenario, right? But that is because we are in a transactional world. So the other case would be if I am using it for an analytical workload, where once the data is written once, it is never changed, right? And everything that happens on that data would be analysis, reads. In that case, I want to design for efficient reads and not writes. I want to design for efficient reads. And in that case, embedding would be the way to go. So two things I have mentioned. You want to look at your context. Am I doing this for transactional workload, or am I doing it for analytical workload? And that helps you make the decision. Should I use a object embedding, which is a denormalized way of doing things, or you want to use object referencing, which is the normalized way, using the relational design word. Now, the last one is the frequency of writes and reads. So I talked about a post and a user before. Now, in a social media application, the user is something that's frequently will change. So what the post most frequently will not change, right? It could change, but very rarely. Let's take the Twitter example. You tweet, you're not expecting it to change. So when something is going to change so often and it is related to some other things that will not change often, you want to do object referencing, because you don't want to keep that change in so many places that would affect operations, another update operations. So you look at things that will change and things that will not change. Coming back to our data sets, you see the test results are done. We know they will not change, right? So we can do all kinds of denormalizing that we want to do. And to be frank, that is what we did. So we are going to convert this well laid out entity relationship model. We're going to represent it with a very richly nested object that looks like this. So a test results will definitely have test types. So you want to see the type of test, the outcome of the test, and the FWARE type. If it passes, we're not going to have test items. But if it doesn't, we are going to have one or more test items. Now, each test item is going to have a failure location and a test detail. A test detail is going to have a parent item group, and that item group can have another, a child item group can have child item group. So you can just have that self-join them. So instead of having how many number of tables like we had in a relational world, we are now going to have just one document called test results, and it will now be richly structured, right? So that is the conclusion of our model, because number one, once this data is generated, it will rarely change. That is one. Number two, MongoDB as a document data store can handle rich data structures, so we can literally take as much. Remember, MongoDB is a schemaless database. You can just start writing your data in without the constraint of defining a schema beforehand. So now that we've seen our new structure, we're just going to have one object called test results that's going to contain everything. So we're like merging all the whole entity layouts that we saw in MySQL into one rich object. We did that with the help of Spark application. So we're not reading it from the database and writing it into MongoDB. Instead, we're reading it from the files that we read. And I'm just going to walk you through the Scala application that was used to write it. By the way, it was built using SBT, but let's focus on the main and let's pick up a few things. Number one is that I defined the schemas of the large files in JSON. Now, the reason I did that is because when you read a text delimited file in Spark using Spark 2.x, you can infer the schema. However, that's time consuming. So if you want to improve the performance of your application for the kind of operation where you already have the schema sort of predefined, you can generate the schema during development time and ship it with your code. And that is what I have done. So if you come right to the main, you have resources, you have schemas, and I have all these schemas right here. I have defined the schemas, and what I'll do now is I will now read the data and pass in the schema. I read the schema as a struct type, and a struct type in Spark, Apache Spark, is the way you define a schema in memory. So I define it and I read all the CSV files. The files are pipe delimited, so you can see all that. Everything else was just how we read the file, the parameters you pass at runtime. Once that is done, we will build two kinds of objects. Now at this point, I want to go back to modeling. When you model for NoSQL databases, you have to look at your usage pattern. So I'm going to jump one step into number 3 objective. We want to look at the aggregation queries that we are going to come across. Even though MongoDB supports ad hoc queries, you really want to be guided by your usage pattern, right? Let's look at some of those queries. I looked at these queries and I saw there were two general classes of queries. One of the queries was looking at the item detail and the entire hierarchies of possibilities of failures. That is what it literally means. It has nothing to do with the test result or the test item. It just deals with test item details. You can reuse it every single time. And the idea is that it serves as a way to define what failures are, or item details. And that is the part that is hierarchical. So I look at this query and say, look, this query has nothing to do with a vehicle. So we could have a collection, right, which is the same thing as tables in relational database for this kind of data, because it literally has nothing to do with a vehicle. It has nothing to do with an instance of the test. It's just it's a system of defining test results and reason for failures. So it required me to build that. Then I looked at the other queries. This is a lot has to do with test results, and this also had to do with test results. So I ended with two different collections. The first collection is the the test details, and it's a definition of reason of failures and the hierarchies in defining test failures. And the other one is the test results that happens every time on cars. So you see, we built a case for the way we want to arrange our documents and collections. So let's come back to the code. We now read our lookup tables. Remember, we want to read all these lookup tables and we want to merge them into something that should look like this. So we now start building the MongoDB documents. Remember, for the item group, right, what we have is a self join, and I used the query to see how many self join do we do, what's the level of hierarchy they get up to, and we see they got up to five hierarchies. So that is why I opted for building 1, 2, 3, 4. Yep, it's not correct enough, and 5. So that hierarchy. And this is what I just did. I created a data set and I created like 4 other aliases of that data set. And I implemented all that join and projected the data renamed it appropriately, and I write it to MongoDB using the MongoDB Spark connector. Right, this MongoDB Spark connector helps you to see the MongoDB world as to it unites the MongoDB world and the Apache Spark world, where you deal with data sets and data frames. So it's like bringing your structured world to the structured realm. And another thing I want you to note here is the write consent. Now, MongoDB has flexible consistency level, and you can decide to improve or reduce the consistency requirement to improve your performance. Now, W1 write consent means that we only want, in the presence of replication, right? In the presence of replication, we only want an acknowledgement from a replica before we say that write was successful. If I want it super fast, then I would say I don't want any acknowledgement. And you know, with that setting, it could be data loss. But now I'm saying I want just one replica to acknowledge and I'm done. You can say I want all the replicas to acknowledge, then you will have slower writes, kind of, because everybody must speak before that write is acknowledged as successful. Having done that, we use the mongospark.save and we write the data frame that we've just created to MongoDB. So that just does it. Then once we've done that, we now build the bigger one, which contains a number of test items. So we first enrich test item. Then we now say for all tests, we group by and we create one huge test items, a lot of them. Then we also do the same thing to test results and we load all the test items. So this is like an array in an object that also contains other struts. We call them struts. So like I built an object, another object, another object, another object, and this is that big array. And we're going to see how it really looks like. Now, when we're done, we save this enriched object into the MOT database, the test results collection, and we do it in a batches of 10,000, and we also acknowledge, we do only one acknowledgement. Okay, that is it in a nutshell. By the way, if you go to my GitHub repository, I'm going to provide a link. All the codes are here, and you can see us modeling this data in MongoDB. How did I build this application? You use SBT. I also added the SBT assembly plugin so that I can bundle the MongoDB Spark connector library along with my application. By the way, I am using HDP Sandbox, and with HDP Sandbox, I just used a shell. I just opened an SSH shell to the sandbox, and this is the command that is used to run it. So this is the job that I copied into the sandbox, and I am before I show you this, let's do HDP. So you would see all the data, the test result 2010, test result, test item 2005, pretty big. Test result 2010 is 2.9 gig, and all my lookup files. So these are the files, the raw files that are on HDFS, and I'm reading them using Spark. And the command is this. So I configured my MongoDB on the host machine and the HDPs on the sandbox, and need I show you how I made that possible? You want to go to the config, MongoDB config, and bind it to 0.0.0. By default, it's bounded to localhost. So having done that, the IP for my host machine is what is there, and I am passing all these HDFS path parameters. And another thing I did was set the spark.sql.shuffle.partition to 300. By default, it is 200. But if you notice, this is one machine is running everything that I'm running, and it's pretty large data set for the machine that I'm using. So I increased the partition to avoid running into out of memory error. right? I increase the shuffle partition for that purpose. Okay, so all I have to do is execute it, and it starts running against my MongoDB database. We now have the MOT. Now with MongoDB, you don't have to create the database upfront. You don't have to create the collection upfront. Once you just do that, MongoDB creates it for you. And when I go in there, I have all the stuff I need. So if I come right here, I see the item details. This is the one I talked about that I'm just building for. I am building without the definitions or without reference to the particular vehicles themselves, just the definition of failures and the reason for refusal. So I would say db.item details. Let's see how many records we have there. 12,595, not much. Let's look for 2010. I think it should be the same because it has nothing to do with a vehicle. It's just a general definition, so there's no big deal there. If we look at test results, test result itself, count, you see we have, this is the 2005 version, we have 7.4 or about 7.5 million records. If we look at the 2010 version, we have about 36 million records. Okay, so just tell you up front, don't be disappointed if while running the Spark application it takes time, right? It will take time just because you're using a single machine and you're doing a lot of joins. Remember, for the size of this machine, this is a lot of data. So like the 2010 took me almost an hour. The 2005 took me about 15 minutes thereabout. But just let it run. In the same way, if you were uploading it into MySQL, is still going to take you a long time. What you're using the load data command is still going to take you a long time. So it's just a function of our working environment. Okay, so we have the data. Let's just see some things. I'm just going to say test results, and let's pick one record. Find one. So you can see this is the rich data. We have the test results. We have a date data type. We have number data type. We have string data type. And you can see test type, which is supposed to be a lookup. We have meshed it as an object. Test outcome, fuel type. And this test result is a pass. So we don't have test items. We don't have the failures because it passed. So we don't have test items. Let's pick one that has test item. I'm going to say I'm adding a where clause. So F, and the test result is outcome dot result code, right? So I'm going to say outcome dot result code. Outcome dot result code. So you can see we have how many test items? We have 2 test items, and we still have where types, outcome types. Let's see, outcome is failed, so it failed the test, and these are 2 items in the card that failed. So we have a very rich data structure, and the cool thing about this is let's compare MySQL with MongoDB. If MongoDB was supposed to write this object, it would do it with one single write operation, one single write. But if we're going to do the normalized or the normalized version in a MySQL operation, right, it's going to use transactions to write into at least 2 tables, the test results and the test items. So by breaking things down, we improved write efficiency, right? And we have now a data set that we can now begin to perform aggregation operations. Now we're going to look at writing these queries themselves. So what I do is I want to compare queries for MySQL with queries for MongoDB. Now the simplest of all, let me start with a simple one. The one that just says, let's look at the error definitions, so the item details. Because these are normalized tables in a MySQL environment, we have to join at least 2 tables in one hand, and in the other hand, the second table will join it with itself 5 times. 1, no, 4 times. 1, 2, 3, 4. We had to join it with itself 4 times because we want to get that hierarchy. But it turns out that we already built that hierarchy into our denormalized table. So we just did a simple where clause, and definitely you expect this to be faster than this, right? So we just run MySQL. Good. We get results, 12,595 records. It's just going to fill up the whole place. And we want to do the same in MongoDB. This is how you do it. You said find, and you put your where clause criteria. In this case, I'm saying don't project the MongoDB generated primary key and give me all these ones. So this is the way you project the columns you want from a query, and this is the way you suppress a column in MongoDB. So I'll copy this and run it here as well. Run it. Cool. You can see with the if I want more result, I type it, so it just iterates the internal cursor for the result set. Another thing I did not say is that remember when we built these tables like test details, item details, and group, if we go back to the DDL, right, we already set index, but we've not done that for MongoDB, right? You want to try adding indexes to your MongoDB collections and see if you get anything positive. Okay, that said, let's look at a more involved query. And this query, we want to see the initial completed test volume by setting class. And from the MySQL perspective, this is what we get. And it's fairly easy to understand, right? So aggregate, give us a count using these 2 dimensions, class, test class ID and test results. And with this number of where clauses and group by that. It's something everybody who've used MySQL is easy to understand, right? You can also change this to 1, you get the same result. If you run these in MySQL, you get, that's it, and you get your result as you wish, right, in 4.51 seconds. Now the same query in MongoDB is something like this. Now for aggregation queries, MongoDB uses what we call the aggregation framework. And the aggregation framework uses a pipeline of stages, and each stage uses a particular operator. So what is the pipeline? These are the pipelines, right? And the aggregators are, the operators are match, project, group, project again. So you just arrange them as you need to. If this is the first time you're using the MongoDB aggregator framework, it can be daunting because you're like, what is this, right? Or you want to imagine the where clause. Look at and. I did a lot of and right here. And there's another in operator, there's another and operator, and look at how we did between. Yeah, it can be daunting, but once you just get used to it, you can see it really improves the way you do the possibilities of things you can do, right? So let me run this query in MongoDB. By the way, our test result collection that is running about 7.4 million records is totally unindexed, so we're going to have full table scan compared to this query that we don't have full table scans. We don't, because we already did that. Yep, and we get the same result. So let's see, volume 80, test 5, pass with rectification as station. We should see pass with rectification as station 580, something like that. Cool. That's exactly what we're talking about. So the same query produces the same result. Remember, this is unindexed. Definite. So we are doing full table scan. We've got our results, and we have the third query. So with this query, I'm going to say sometimes it looks like, what are we doing? So let me show you how you really want to write aggregate queries, especially walking through the stages of the pipeline. And because it's going to be difficult to just debug this, let me show you what I typically do. and that is to execute them stage by stage to see the results. It is difficult to do that on command line, and that is why using IDEs are very helpful when we do work with MongoDB. For instance, I'm just going to put all this stuff here. I hope you can see them. And one thing you can do is execute them stage by stage. For example, I am only going to start from, I'm just going to cut out this stage, and then I'll run it and check the results. Yep, is this what I want? Yeah, it looks like what I want. So what's the next move? The next move is I want to unpack this internal array. So that is basically what we did here with the unwind statement. So unwind statement will do the unpacking, and we'll run it and we say, did it unpack it rightly? Yes, it unpacked it, but it's not perfect enough. What's the next stage? We want to retain this, and F and P only. So we just look for anyone that is not F and P, and those ones we go. So I would run this part of the query, execute it, it works, it looks good. Now the next thing is I also there's no array again, so there's nothing to unpack. I now want to flatten the results. Instead of working down through the nested through the nesting, I want to only see it as two objects. All of a sudden it's now two objects, right? Because I have used the projection stage to like flatten that nested structure. Then when I'm done with that, I will do something that's a lot more involved, which is now group by, and the group by will now do add to set. So it's going to create like a bucket, and it's everything for this item name. It will do a count and it will add to set. So if I execute that, something is wrong, undo. Cool. So that is how you debug a so look, that's what we got. This is the set itself, right? And why did I use a set? Remember, if you add to a set does not contain duplicates. A set doesn't hold duplicates. And remember, when we were doing the MySQL stuff, we did something like count distinct. So we wanted to take out duplicates. So you literally have those tools to kind of fashion your queries in MongoDB, and the tools are there. It's daunting at first, but when you start understanding this rather cryptic way of writing aggregation queries, you become familiar with them, and it fairly becomes cool. So IDEs are helpful. This is a free one, Robo3T. You want to see also Studio 3T or Mongo Compass. Mongo Compass you can download from the MongoDB website. Okay, that is what we have. I hope you've picked something from it. Let me know what interests you most in this demonstration. Is it the Spark side of things, or is it the MongoDB side of things, or is it the modeling and able to relate from one world to the other? And last but not the least, we also find that MySQL in version 8, which came out I think last year, has now added the ability for us to build in terms of documents and not just relational model. So you can use MySQL as a document store. And if your intention is to use MySQL in a traditional SQL way, then you forget about this feature. But if you want to start thinking in terms of collections and documents, then MySQL is there for you. It's new. I haven't really seen much production feedback based on it, but it's something to look out for, especially for those who have invested a lot into MySQL infrastructure. Okay, so this is where I'd like to end this demonstration. Let me know if it's been good. You can subscribe to my channel if this is the first time. By the way, in the middle of next month, I'm coming up with a new course that covers about 8 different databases. NoSQL databases, SQL database, hands-on, totally hands-on, and we also include Hadoop and Kafka, and it's a journey through database technologies. And we'll look at MongoDB a lot more in details in that course. So from me, thank you for watching this video, and hopefully I get to talk to you some other time.